Okay, so let's see what this particular experiment is about. As you can see, as we have said, each experiment is a design, simulation, and then breadboarding and measurement of the circuit. So in this case, we have another, in terms of component count, a fairly simple circuit, Schmitt trigger oscillator. And what you have to do is design this particular oscillator for a frequency of 1 kilohertz and a duty cycle of 50%. Right? And as usual, after you do the design and simulation, you come to the lab, you breadboard it, you measure the oscillator's performance here. So let me describe this particular oscillator then. So the block diagram of the oscillator is shown here. So this is your Schmitt trigger, which I'm sure most of you are familiar, but we'll discuss it in a minute. So this is your Schmitt trigger. And along with Schmitt trigger, we have an RC circuit here, which is connected. The one end is connected to the output of the Schmitt trigger. The other end goes to the input of the Schmitt trigger here. So to remind you, the Schmitt trigger has a characteristics, input-output transfer characteristics, which is shown over here. And what is very interesting about this particular device, Schmitt trigger, is that it shows a hysteresis. If you note, if you start from a very low input voltage here, what happens is, in this case, it's an inverting Schmitt trigger. So if you start with very low input voltage, let's say VC is 0, input is 0, then the output is going to be high. And we call that value VOH. Now, as you increase the input, the output, as you can see here, according to the arrows here, the output remains high till you reach a threshold value, which we call as VIH. And once the threshold value is reached, it switches to a low state here. So from VOH, you go to a value which is V0L. All right, and it stays V0L as you go, as you increase VI more than VIH here. So far it just looks like an inverter. It starts from a high value at a certain threshold value here. It switches to a low value here. But what is very interesting is that normally, if you have a circuit, if you have a simple inverter, when you reverse the input voltage here, normal inverters would come back and follow this particular line here. In this case, it doesn't. What happens is it comes here, and at this value, it doesn't go up. It remains low. It remains low till you reach another threshold value here, which we call as VIL. Now, don't confuse your VIH and VIL with digital inverters that you are doing in 370, VIL, VIH, and these are not the same VIL and VIH here, okay? So anyway, as you decrease, a voltage comes, VIL comes, and at that point, the output switches back to high value here. And then as you go further, it remains VOH here. So what you see here is that this circuit has a memory. It has a memory here, and it shows a hysteresis that you see here. So now, if you have this Schmitt trigger, this kind of a characteristics, we can make an oscillator by simply connecting an R and a C in this particular manner here. Now you can see what happens here. So this is Schmitt trigger, and with an R and C, what would happen is the following. Let's imagine that initially the capacitor is uncharged, 0. All right, so we are starting here 0. Now, if it is 0 here, you note that Schmitt trigger tells you that if the input is 0, the output is going to be high here, V0H. Right? So the output is high here, V0H. And so we have V0H connected to R and a C here. So what happens is the capacitor starts charging. You have a simple RC charging here. Right? And it starts charging here. It starts charging here. And you know that what is happening to the capacitor voltage, which is same as here. It starts charging till it reaches VIH here. So till it reaches VIH. The moment it crosses VIH, what happens is the Schmitt trigger changes state. The Schmitt trigger now goes to V0L here. And once it goes to V0L, and remember V0L, of course, that you see here is smaller than VIH here. So now this is V0L here, and VIH, the capacitor, is at a higher value. So what happens is the capacitor starts discharging. So this C here that you see, it starts discharging through R here. So it starts discharging and keeps on discharging. Now what is happening is you're coming back, you're retracing the path. From VIH, you keep on, as the capacitor discharges, the voltage keeps on decreasing till you come to VIL. Once you come to VIL here, the Schmitt trigger switches again. It goes back to high value here. And as it goes back to the high value, this V0 becomes V0H here, and then the capacitor starts charging again, and then starts discharging. So what you will get if you see it on the oscilloscope, of course you're not going to see this particular part here on the oscilloscope. You'll see the steady state. So you'll see something like this: capacitor charging, discharging, charging, discharging, right? And this is at the input here. At the output, Schmitt trigger has only two states: high state and low state here. So at the output, you will see a V0H, V0L, V0H, V0L. And therefore, you have a oscillator. You have an oscillator where all that we have done is we've taken a Schmitt trigger and connected an R and a C, and you get this oscillation. So very simple oscillator, and one can analyze this and show how to choose the value of the charging time. This is the time when the capacitor is getting charged. So we call this the charging delay, TC. And this is the time when capacitance is discharging. We call it the discharge time, TD here. And the total time period, as you can see, is TD plus TC here. And the duty cycle would be the time for which it is high divided by the total time period. And so that's the duty cycle. Okay, so a very simple operation. But the experiment is not going to be as simple as this. We'll see where the complications are. Okay, so let me very quickly derive an expression for the charging time and the discharging time under the following simplifying assumption. And the assumption is that when I'm charging, note that when I'm charging, this voltage is V0H, and this voltage initially is VIL here, and is charging here. What I'm assuming that as the capacitor is getting charged, note that the charging current will come through R here. As it comes and charges the capacitor, I'm assuming that the Schmitt trigger does not draw any current. Okay, Schmitt trigger does not draw any current, and therefore my charging is simple R and a C. Simple RC charging, for which all of you know that, you know, when you have a simple RC circuit, any voltage or current follows this exponential law. The xt could be a voltage, could be a current. So xt equal to x infinity plus x0 minus x infinity exponent minus t by tau. And so with that, we can write down what will be the capacitor voltage here. The capacitor voltage, Vc, will be equal to the voltage of the capacitor if it gets fully charged. Now, who's charging the capacitor? V0H here. So if it gets fully charged, the value will be V0H here. Now, x0, starting value, as you can see here, is VIL. So we put VIL here. The final value, steady state value, is V0H. We put that here. And we put exponent minus t by tau, which is nothing but RC. So we put in here, and note that the charging will stop at VIH here. When the voltage reaches VIH here, so if I put VIH here, I'll get the charging time. Okay, so all you do is, for the capacitor voltage, you put VIH and solve, and you'll get the charging time, which is equal to RC, and depends on all these parameters. Okay, and similarly, the discharge is also very similar here. In the discharge case, the capacitor is initially, remember, at VIH here, and the output is low, so the capacitor is discharging towards V0L. So capacitor is discharging towards V0L, and it will stop at VIL here, and so if you, in this discharge expression, if you put VIL, then you'll get the time it takes for the capacitor to discharge, this TD, right? And so you get TC and you get TD, so you have all the expressions here. Except that we have a simplifying assumption that the Schmitt trigger is not drawing any current from the RC circuit here. Okay? So that's the behavior. Now, this is the Schmitt trigger. You can make Schmitt trigger in many different ways. So we have a Schmitt trigger, which is not a very good Schmitt trigger. Okay? And that's why it will cause problems here. Let me explain how this Schmitt trigger works. It's a very simple Schmitt trigger. Two transistors, Q1 and Q2. And how many? 1, 2, 3, 4, 5 resistors. Okay, so very simple to make in the lab, and it's very simple, but as you will see, it has issues. Okay, so let's see how this Schmitt trigger works. All right, so keep this picture in mind here. This is how my circuit should work here. Okay, so when the input is low, it should remain high, and then switch at VIH. Then when you come back, it should not go up at VIH. It should remain low, and then come up at VIL. So that's what we are looking for. So let's say, so what I'm interested in is finding out what are the expressions for V0H, V0L, VIL, and VIH, okay, from this circuit. So to find V0H, I apply a very low voltage here, say 0, Now if it is 0, now note if it is 0 here, and if I look at this transistor Q1, I have a 0 here. If I look at this particular input loop here, obviously Q1 is going to be off. I don't have any voltage. I need at least 0.7 volts to turn it on. I don't have any voltage between this point and this point. My Q1 is going to be off. Alright, so Q1 is going to be off. Fine. If Q1 is off, it does not draw any current, which means that if it doesn't draw any current, then the only current flowing through RC1 is the current which starts from here. Q1 will not draw any current, so it's the current which goes into the base of Q2 here. And base current in general is not very large. So what would happen is this value is going to be high. Say this is 5 volt, this value is going to be close to 5 volt, unless you choose RC1 very, very large. Okay, so this value is going to be high here, high value here. So now if you look at Q2, we have a voltage here which is applied to the base, which is high, let's say 5 volt, and this is going to the base here. So what this will do is it will turn transistor Q2 on. Because I have a voltage here. Right here I have a voltage close to 5 volt here, and this 5 volt will go, and I need only 0.7 to turn it on, and so my transistor is on. And all of you know, when a transistor is on, it can be in two possible states, forward active and saturation. Now if I choose my resistors RB2 and RC2 and all that properly, what I can do is I can drive the transistor into saturation. So what will happen is, let's assume that our choices are correct and the transistor Q2 goes in saturation here. Okay, so it is on, we realize that, but let's assume we'll design it like that, that it goes into saturation region here. Alright, if it is in saturation region, you know that the voltage across Q2 is going to be 0.2, right? And therefore, note how the current will flow. The current will start from the supply, flow through RC2, the drop here is going to be 0.2, the current is going to come here, and then eventually flow into RE. That's how it will flow, okay? The direction of current flow. Now, we can write down what is the voltage at this particular point here. Because note the current is going to be, if you go through this particular loop, output loop here, the current is going to be VCC minus VC sat, that's the net voltage, divided by RC2 plus RE. That's the net resistance in this particular branch. So that's the current, and current multiplied by emitter resistance here will give you this particular voltage. Alright, so we have this voltage at this particular node here. Okay. Now, if this is the voltage at this particular node, now remember what is happening is output is high. The output is over here. Now, as I apply my input, as I change my input, how much voltage do I have to apply to turn this particular transistor Q1 on? Well, if you look at the circuit, then you realize that to turn transistor Q1 on, I need a base emitter voltage 0.7 plus this drop here. Right? These are the two elements here. So that's why this transistor Q1 will turn on, which is the place where VIH is high. Okay? So that will be the value which will be equal to VB on, which is 0.7 here, plus this value here, which is given away. Okay? So now, actually, now you must be wondering, why is it so abrupt? Something very interesting happens here. If you look at, so suppose I get, let's say this VIH value, you know, if you do the calculation, let's say it is 3.7. Okay? 3.7. Now, suppose you come very close to 3.7. Alright? You're increasing the input value here steadily from 0, and you come close to 3.7. Now, what will happen is, if you look, this transistor is turning on. Now, if this transistor is turning on, what will happen is, what will happen? As this transistor turns on, note that as this transistor turns on, you start to draw current, right? Q1 will start to draw current. And as Q1 draws current, what happens to this node voltage? It starts to drop, right? And as this voltage starts to drop, what does it do to Q2? This is the voltage which is turning Q2 on. So as this voltage starts to drop, it tries to switch off Q2, right? That's the direction in which it is going. So what happens is, as this transistor starts to turn on, this voltage drops, and as this voltage drops, this transistor begins to switch off, and the current here drops. Now, as the current in Q2 drops, this current Q2 is what is causing this particular voltage here. So what happens to this voltage then? this voltage begins to drop. This voltage begins to drop here. Now keep in mind another thing. RC1 is larger than RC2. So what happens is, as you start to switch this transistor Q1 on, this voltage drops. As this voltage drops, Q2, the current in Q2 starts to drop. And as current in Q2 starts to drop, this voltage begins to drop. And if this voltage begins to drop, what happens to the forward bias on this voltage here? Note, you have applied 3.7. This voltage is fixed and this voltage is dropping. If this is dropping, then it means Q1 is getting more forward biased. And as it gets more forward biased, it draws more current. And as it draws more current, what happens to VOH? VOH falls even more. And as VOH falls even more, the current in Q2 falls even more. And then this voltage increases even more. And so you are saying there's a positive feedback. There's a positive feedback action here. And what happens is you get this very, very sharp change here. The moment you start to turn Q1 on, the Q1 turn on, and we call it a regenerative action, a positive feedback action here. And therefore, very sharply, Q1 turns on and Q2 turns off. Okay? You can see here. And I'll show you the simulation result in a minute here. You can see a simulation result. You can go and take this particular circuit in microcap and see what is happening here. This is ICQ2. The green one is ICQ2 here. And the red one is ICQ1. Okay, the first transistor. Note that the first transistor is turning on. The second transistor is, the current is falling. And note how sharply it goes. In fact, in microcap, I try to, make this voltage 1 millivolt, 0.1 millivolt. I still can't see a slope. I can't see a slope here. Okay, it's just abrupt. Very, very sharp here. All right. So it sharply drops here. Transistor Q2 turns off. Current goes to 0. And transistor Q1 goes up. And the current goes here. But note, the circuit is designed such that the current that Q1 eventually carries is smaller than the current that Q2 carries. And so this is what happens then. That this transistor Q2 abruptly switches off and goes into cutoff, and Q1 then turns on. Okay? Q1 turns on, and we choose again resistor values in such a way that when Q1 turns on, it goes into saturation. Okay? All right, so one can then, so I've already told you the value VIH at which your transistor Q1 turns on and Q2 turns off. So that's VIH expression is over here. And once we know VIH here, this is VIH also, because the VIH, if you note, is this voltage plus the 0.7 volt here, which is same thing as this voltage plus 0.7 volt here. So this point is also, when the transistor Q2 is on, this point is also at a value close to VIH here. So if this is VIH, now I'm talking about this portion here. If this is VIH, note that the current is flowing like this here, okay, into the base. Transistor Q1 is off, Q2 is on, and the current is flowing here. And therefore, I can write what is V0H. At this particular point, note that V0H will be equal to VCC minus the drop in RC1. And what is the drop in RC1? It is the current which is flowing in RC1. And what is the current flowing in RC1? It is the base current. It is the base current which is flowing there. Okay. So anyway, we know this point VIH. We know this is VCC here. So the net current which is flowing into the base is nothing but VCC minus VIH divided by RC1 plus RB2. That's the net base current that is flowing here. And so once we know the current flowing here, we know the drop in this particular resistor, we can calculate what is V0H. All right. So we have now two expressions. We have an expression for VIH and we have an expression for V0H. But note that in this particular circuit, we have to design it in such a way that this transistor is in saturation region. And to do that, the condition for saturation, let me remind you, is that beta times the base current divided by collector current must be larger than 1. In saturation region, IC is not equal to beta IB. IC is actually less than beta IB. And the larger this particular ratio, the deeper the transistor is in saturation region. Okay? If you make this ratio, let's say 1.1, the transistor is in saturation but very close to the edge. If you make this ratio 5, the transistor is fairly well into saturation region. If you make it 20, it's deep into saturation region. Okay? So how hard you drive the transistor depends on this particular ratio here. Okay, so you have to make it substantially larger than 1 here. Try a value of at least 4 or 5. Okay, to keep to be on the safe side. All right, so that's so you have to satisfy this particular constraint, and we have expressions for IB2 and IC2, which translates into this kind of an expression. So IB2 we know what is the base current here, and IC2 we know what is the current that flows in the output loop here. So this condition can be written in this manner. So this is when I have this particular part here, when I have V0H and then it switches and I get a value of VIH. Now when I come back here, then something similar happens here. Okay, so now what is happening is this value is high here, this value is high somewhere over here. The transistor is in saturation, Q1 is in saturation, and Q2 is off. And this value now, note at this value. This value will be equal to, if this is saturation region, the net current flowing in the output loop is VCC minus VCE sat divided by RC1 plus RE. That's the net current flowing here through this transistor. And so this voltage is equal to the current multiplied by RE. Now, interestingly now, as I said, we choose RC1, which is larger than RC2. Okay, so now this value that you see here, is smaller as compared to the case when Q2 was on, because I've made RC1 larger than RC2. So what happens is, so this is the value here at this particular point here. This transistor is on. So now when I come back, when I, voltage is let's say 5 and I start coming back. And as I reach this particular point here, I don't go up. Why? Because this value is different now. This value has become low. So what happens is I have to keep on reducing the value here, keep on reducing. And when will I switch off Q1? When will I switch off Q1? When the voltage here at this particular point drops below 0.7 plus this value here. Once the voltage begins to drop below this particular value, Q1 will start to turn off. And so my VIL is a point where the voltage at this end is nothing but 0.7 plus the drop here. And therefore we write here VIL. And V0L is also very simply written because, V0L is this particular point. We know what is the current flowing in this branch. So the value here is nothing but VC sat here, 0.2 plus the drop here. So both these values, VIL and V0L. You also obtain, and remember, we have to keep this particular transistor in saturation region also, which means that beta 1 times IB1 here divided by IC1 must be greater than 1. Again, choose a value at least 5 or 6 here. And this again, we can write it here. Now again, note what happens is the moment you start switching off this particular transistor here, as you start to switch off as you go here, then what happens is the collector current of Q1 starts falling. And as the collector current of transistor Q1 starts falling, this value goes up. And as this goes up, it starts to turn Q2 on. And as it starts to turn Q2 on, then this voltage starts to go up. And as this starts to go up here, Q1 further turns off. And as it further turns off, this voltage further goes up. And again, a positive feedback action happens. And then very sharply, it goes to Q1 will turn off and Q2 will turn on. So you get very, very sharp transitions here and very sharp transitions here. So that's how your Schmitt trigger works. Okay. And you have expressions for the values of Schmitt triggers are VIH and VIL threshold values here. And you have V0L and V0H, which are the low and the high values here. So we have expressions for all of them. And these expressions that you see here are valid only if you ensure that this condition is valid. Because we are assuming that when a transistor is on, it is in saturation region. So you have to make sure that this condition is satisfied, and similarly the other condition here. So these are the equations for the Schmitt trigger. All the equations for the Schmitt trigger are summarized here. 1, 2, 3, 4, 5, 6 equations are there, and using these 6 equations, you can now find the values of RB1, RC1, and all of that. Once you decide that you want a VIH of so much, VIL of so much, V0L of so much, V0H of so much, once you decide the values that you want, you can use these equations to determine all the values here, RC1, RC2, and all. Okay, and we already have these equations. So our complete oscillator then becomes that you take this point here and attach your RC to the input of the Schmitt trigger. So that's the complete oscillator. We already have expressions for TC and TV. Okay. So that's the simplified description of the oscillator. Now, let me show you where the problems are. Okay. Now, this is what is very interesting about analog circuit. A very simple circuit that you see here, and it can turn out to be very interesting. Okay. So a lot of interesting effects can occur in a very, very simple circuit. Now, let me show you what happens here. So we have all these equations. Now, if you look at these two equations, VIL and V0L, if you examine both of them, what you see here is that the second term is the same in both of them. In the first, this is 0.7 and this is 0.2. So immediately we note that VIL minus V0L is about 0.5. Okay, so the two are not independent. The moment you choose VIL, you also choose V0L. The two are related together. All right, so that's 0.5. Now, for this oscillator, assuming that no current is flowing in here, we had this equation, TC and TD. We want a duty cycle of 50%, which means that I should make TC equal to TD. All right, so equate these two values here. If you equate these two values, do a little bit of algebra, and from there you can show that in order to make TC equal to TD, duty cycle of 50%, the condition is VOH minus VIH should also be 0.5. That's the condition that you will get. Okay. Now, which makes it further our problem simpler, which means that I have, as far as Schmitt trigger is concerned, I have only two independent specs. I have VIL and I have VIH. Once I choose VIL, my V0L gets fixed, and once I choose VIH, my V0H also gets fixed because I want 50% duty cycle. Okay, so these are the only two independent variables here, VIL and VIH. So now your task is choose some value of VIH and VIL. Okay, well, you have no basis, so let's choose something arbitrary. We know that VIH has to be larger than VIL, so let me take some value here. You're free to choose different values. So I've chosen 3.7. If you choose VIH equal to 3.7, then V0H becomes 3.7 plus 0.5, so becomes 4.3. And I've chosen VIL equal to 2.2, and so that becomes V0L then becomes 1.7. Once you have these values, then you have to go back to these equations. I'm not going to tell you. If you have, maybe in another lab we can discuss how to use these equations to design, but I'll leave it up to you that once I know VIH, VIL, V0H, V0L, I can use these equations to determine the design. So let's say an example of a design is given here. All right, RE, RC1, RC2, RB1, RB2. All right, so I have a design. Once I have a design, then I'll open my microcap. I'll make the circuit. This is my Schmitt trigger. Okay, RC1, RC2, all these are there. And I'll test my Schmitt trigger by applying, let's say, a triangular wave here. Because to test the Schmitt trigger, you have to go up and you have to come back again, right? So apply a triangular wave going up and down, and then you can plot it out, and microcap shows that the Schmitt trigger is working reasonably well. Except that, because the equations are a little bit simplified, note that VIL was 2.2, I'm getting a value 2.245, and further, it is very sharp, but then there are some of these non-idealities that you see here. It's not a perfect, goes down and like the ideal curve that you see here, okay? My VIH design was 3.7 and is coming out, this point is coming out to be 4.02. Again, note, it's very sharp here, but then it starts curving here, okay? So there are some non-idealities here. Anyway, so I have a Schmitt trigger. Now, how do I design an oscillator? Schmitt trigger is done. VIH and VIL are also there. So I take this equation, TC equal to RC, ln V0H minus VIL and all that is there. I have all these values. So when since I'm designing for 1 kilohertz, which means my charging time is 0.5 millisecond. And so this tells me, once I put in all the values, that RC has to be 0.36 millisecond. So again, I have a choice here. So I chose a value of 10K, R of 10K here, thinking that when I put 10K here, it will not, well, maybe the choice is wrong. So anyway, so I chose a value of 10K and it gives me a value of C equal to 0.036, right? So my design is complete. Then I went ahead and put the R here and a C here and these values and no oscillations. It didn't oscillate at all. Okay? Didn't oscillate at all, which means somewhere something has gone wrong. All right? Then, well, maybe I thought the value of R was high. 10K was very high. 10K in series with 2.2K, very high. So I lowered it to 1K. Now, when you lower it to 1K, note that if you make R 1K, then C correspondingly has to increase to maintain the frequency. So when I made it 1K and 0.36 and simulate it again, all right, so these are the changes I made here. Well, it oscillates. Okay, it oscillates, but then what do you see? It does oscillate. Can you see a problem? Duty cycle is? It is, note all the problems here is hardly a square wave, is rising and then becomes like this here and then goes. Duty cycle is definitely not 50%. The on time is maybe 3 times the off time here. Okay, so duty cycle is not getting satisfied and is highly distorted. So now the issue was what is happening here? Yeah, we managed to get oscillation. So, there is a Schmitt trigger here. So you can still take V0 here and Vi here, input here, and you can plot the Schmitt trigger characteristics by plotting V0 against Vi. So when you plot the Schmitt trigger characteristics, note what has happened to the Schmitt trigger. Let me plot both of them together. Forget about this initial part. This is my Schmitt trigger. Note when I don't connect my RC network, R and C. When I connect my RC network, this is what happens to my Schmitt trigger. Note the scales are the same. 5.25, 4.5 here, 4.5 here, 5.2. Almost the same scale. This is the Schmitt trigger when it is not connected, when it's isolated. The moment I connect my Schmitt trigger to my RC circuit, look what is happening to the Schmitt trigger here. What is it telling us? My assumption was, my assumption was the Schmitt trigger was not drawing any current or Schmitt trigger, but the moment I connect the two, I find the characteristics of the Schmitt trigger get totally altered. All right, and this is the problem here. This is the problem that all along, all that I described for you, especially these equations that you see here, these equations, TC equal to these equations that you see here, TC and TD, these were derived by assuming that the Schmitt trigger was not drawing any current. All right, and so what is happening is the following. Okay, I'll show you in a minute. Let's skip that. So basically, these equations that you see here assume that RC circuit and Schmitt trigger do not load each other. Whenever you have two entities, two blocks, and you connect them, in general, both the blocks will affect each other. Okay, unless you take special precaution here. So what is happening is your RC circuit is affecting the Schmitt trigger, and Schmitt trigger is also affecting the RC. Both are affecting each other. Okay, they're coupled together here. All right, and I'll tell you in a minute about this Schmitt trigger, how they affect each other. But before that, let me talk about this is the important concept here. I'm sure all of you have heard of when you do a design, that your design you say is modular. Right? The concept of modularity is very important in design. And the basic idea is that a system, any system that you're designing is made up of components. A system is easier to understand and design when it is built using well-defined but loosely coupled components. Components which are loosely coupled means they don't modify each other when you connect them up. Okay? That's the principle of modular design. And in this case, our design is not modular. When I take my RC here, there's one block, and I take my Schmitt trigger here. As I said, when I put them together, my Schmitt trigger, I showed you how drastically it was getting modified. The Schmitt trigger characteristics totally changed when I connected the RC here. And not only that, the charging and discharging of RC also changed because the Schmitt trigger was drawing currents. So both of them are affecting each other. And that is what makes a design complex. It's not modular. If you want your design to be simple, there's a very easy way of doing it. Don't take your Schmitt trigger that I gave you. You can make a Schmitt trigger using an Opamp. Very simple. You take an Opamp, you connect R1 and R2, and this thing is a Schmitt trigger. And the beauty of an Opamp is that Opamp will not draw any current. Right? Will not draw any current. And if you connect anything to the output of the Opamp, also it doesn't really matter. The Opamp has very low output impedance. So the circuit stays the same. And this circuit you can design in 5 minutes. You can find out what is RC, You can choose any value of R1, R2, any value of R and C, it will work. Okay. So this oscillator is very easy to design. You go to the lab, it will always work. All right. It's straightforward. So it's a modular design. The two blocks R and C that you see here and the Schmitt trigger that you see here, they don't interfere with each other. Okay. But remember, to make it modular, there's a price that you have to pay. The Schmitt trigger that you see here, this op-amp, this is the op-amp that you see here. All right. The op-amp has 20 transistors, 11 resistors, and 1 capacitor, 7 for 1 op-amp. So 20 resistors, and you add along with that all these things that are there here. So now you compare this Schmitt trigger, 20 transistors, 13 resistors, and 1 capacitor. And you compare with the Schmitt trigger that we used, 2 resistors and 2 transistors and 5 capacitors here. So what I'm saying is, yes, you can make the design modular, but the modularity and all that you're seeing here often comes at a price. In order to ensure that the two do not interfere with each other at all when you connect them up, you have to take certain steps in order to do that. For example, you'll have to build very high input impedance here, very low output impedance here, and that makes your design complicated. Okay? And on the other hand, our design is very efficient. Our simple 2 transistor design. So if you take steps, if you understand it well, take care of all the loading and everything, it will work. This is an example of a Schmitt trigger oscillator that was designed, and I'm sure all of you will design as well. So you do get a nice Schmitt trigger, and this is the oscillator that you see here. There are complications. It's not a very good design, but it does oscillate, and the duty cycle is close to 50%. You can adjust it. You can get very close to 50% also. So you can make a design which is very efficient, but it will take you effort to design. All right, because of all the tight coupling between the Schmitt trigger and the RC. Okay, so what you can do is you have to design the Schmitt trigger oscillator that I'm talking about. In addition, you can also design this side by side, this particular one, and you can see how well this works as compared to the other one. Okay, so coming back then, how are the two loading each other? Okay, and that's why I said this is what makes this very, very simple design. I mean, it's simple in terms of number of components interesting because of the the interconnections between the elements and the effect that each one has on the other one. Okay, so what happens is, if you note, let's look at the complication that occurs here. So now note that what happens is, when I took my Schmitt trigger, remember I assumed that the current that was flowing here was flowing in this direction. Right? The current was flowing here. Remember when I said this transistor is off, this transistor is on, and then the current that is flowing here is the base current. Right? Base current. But now suppose I connect this RC also. Now what happens is, this RC has to charge. And as it charges, it draws the current. This transistor is off, so it doesn't matter. It's not drawing any current here. But this RC has to charge, and it draws current. And where does this current come from? It comes from here. And as it comes from here, what happens to this voltage? It drops. So the moment it starts charging, that you see here, it starts charging, this voltage gets affected. VOH starts to drop. And if VOH drops here, the other things may also drop. So that's the effect that we are talking about. Now, if you want to avoid loading, what you have to do is you have to make sure that this current is much smaller than the normal current that you have. Okay, so basically this current that you see here, the current that flows into the RC is this VOH minus the capacitor voltage divided by R here. Now what you want to do is you want to make sure that this current is much smaller than the normal current which is flowing here. If you don't connect your RC, the normal current which is flowing here is VCC minus VOH by RC1. So what you have to do is you have to ensure that the current which is flowing through this RC does not is much less than this particular value. Okay, and then you can simplify and write down this particular equation. Similarly, what you have to do is you have to ensure that when the capacitor is discharging, this capacitor C discharges through this R. Now, it's discharging when this transistor is on. So this is drawing current. So you have to ensure that the discharge current is much larger than this current. Otherwise, your capacitor is not discharging through R, but is effectively discharging through RB1 and the transistor. So you get a constraint which is given here. You can see it, and you get another equation here. So now what you get is, I'll skip some of these, you can see here, you get these equations here. All right. This is the equation for the Schmitt trigger. All these equations for the Schmitt trigger. This is the normal TC and TD. And these are the equations that are needed to ensure that your Schmitt trigger and are not interacting that much. They're not loading each other. So you have now all these equations in front of you, and you have the specs, and now you go ahead and enjoy yourself. Okay? All right. So let me stop here. I think we're running out of time. The questions regarding the midsem, if you have any queries. Okay.